Right, okay, so this first question, I quite like this question actually, because they're testing your knowledge, but they're actually, they're doing it in quite an interesting way. But you can see that they're talking to you, right, about the CPU. So we've got some basic things, but remember we have got to spell these things correctly and we've got to say the right thing. Okay, so CPU, Central Processing Unit. Alright, so we've got to make sure we're doing that. It is part of the computer that fetches and executes that's the only thing it executes, remember? So we're testing that. Do you understand how these Harvard CPUs work? Now it said that are stored in. There was a load of wild answers on this, but remember, instructions that the CPU can execute are stored in memory, aren't they? Main memory, primary memory. Now they were quite generous on the mark scheme on this. They allowed you to put registers. They allowed you to put memory data register because that's where the instruction arrives at the CPU. But really they meant in the memory, the main memory of the computer, the RAM. That's what they meant. I think they allowed cache as well, because that's a form of main memory. But it's just about that basic model of the CPU. Right. CPU contains they were nice on this question because they gave you the clue by giving you the acronym out. So it was like arithmetic something unit, or it must have begun with L. So you're looking for clues. L for logic. And then they had this. And remember, these are our CPU components. When we're talking, if you look at the last half of the question, it is about the components of the CPU, isn't it? So it's arithmetic and logic unit and the control unit. So they're just asking about the basic things. Part 2 is where everyone comes unstuck. You know that when they're asking about dual core and single core processors, what they're actually asking you about is, do you understand about being able to execute 2 instructions at once? That's what they're asking about. The only way that a processor with 2 CPUs is going to be quicker is if you can execute 2 instructions side by side. You must make sure that that's what you're saying. You must say that you can actually fetch and execute at the same time. 2 instructions. It's not that you can grab twice as many, because you can't. It's not about speed, is it? It's about the ability. And the other thing you've got to really explain, always when you're talking about dual and multiple CPUs, is it's only any good if your task can be split up that way. If you've got a task that follows that you've got to do A, B, C, D, E, doesn't matter how many processes you've got, that's not going to be able to take advantage of it. But if you've got a task where you can do A, B, C all at the same time, then if you've got 3 CPUs, then wow, you can really take advantage. It's about the tasks. If you've got a task that splits up into separate parts that can all run together, then, and you should know this from like your DT stuff, is that if you're doing like job allocation, if you've only got 1 person, then it's like, oh, do a job, move on to the next job. If you've got multiple people on the team, you can allocate different jobs that can happen at the same time. That's exactly what multi-core is. Okay, so think about your other subjects all the time when you're thinking about these questions. But always, when you're talking about the multi-core stuff, it's about executing 2 instructions simultaneously on a different CPU, obviously. Same when if you start talking about hyperthreading, that's all the same thing. Right, cache. You've been too vague on cache. When we're talking about cache, we're talking about a special small area of memory where we keep our common instructions and data, commonly accessed. We're not worried about how that happens, it's really complicated. Okay, but that's what it contains. So if our instructions that we want to execute are in the cache, they're going to be quicker to fetch than normal RAM. You can't just say it's quicker. It's the fetching that's quicker, because it does not take as long to transfer data from cache as it does from RAM. You've got to do a comparison. You can't just say cache is quicker. Quicker than what? What is it that's quicker? It's the fetch. Reading data is probably about 10 times quicker. Okay? It's all dependent on what sort of cache it is and everything, but it can be up to 10 times quicker. So that the CPU is not waiting for data to arrive. But it will be if it has to go all the way back to RAM. Okay? And it's the problem with cache, it's not asking about this, but the problem with cache, remember, is you've got a limited amount. So not everything can fit in cache. So you can't just say, hey, more cache. It doesn't work that way. Okay, so it is the often accessed instructions and data that are in the cache. If they're in the cache, we can fetch them quicker, which means the fetch execute cycle will not take as long. But only for the things that were in the cache. Okay. We've only got 512 kilobytes, so it's a little bit, on this question, it's a little bit limited. Okay. Right, moving on. This is I like these box questions, but be very careful when you're tackling these box questions. It may be that you've got to identify in the question, it says one or more in each row. So they're not saying, oh, it's just like what. It's not like make a random pattern because you don't know and you're guessing. Be very careful. So you've got to read these carefully. Stores data. Well, they both store data, don't they? They're memory. And remember what's in memory. Data and instructions. That is it. That's all we have in memory. Volatile. You've got to remember which way around volatile. Volatile means we lose if we don't have power. ROM, no, that remembers, doesn't it? So it can't be that. So it's RAM is the volatile one. Data will not be lost when the computer is turned off. So they're switching that round. It's the same question, isn't it? But in a different way. So RAM definitely will. So we're going to tick ROM. Read-only cannot be changed. Yes, we're talking about ROM again there. That's what it stands for, read-only. Stores currently running data and instructions. Okay, so you just got to make sure that you're reading these carefully. Right, the last question on this page, a difference, which means you've got to compare, contrast. You're doing differences. That's the key word. The only what I want for 1 mark, but you had to explain, you couldn't say half of it. So you've got a difference between RAM and flash memory. You've got to remember what flash memory is. Flash memory. What is it, Lewis?
USBs.
Right. Don't say that. Don't say USB. USB actually stands for what?
Oh, memory.
Universal Serial Bus, correct, Kinton? It's a connection system. You must never say that. You can get away by saying USB memory stick, which means a memory stick that goes in the USB socket. Flash memory is logic-based memory that remembers when you take the power away, which is why obviously it works as a USB memory stick. Otherwise it'd be the world's most useless storage device. It's like, oh, it works when the computer's in, take it out and I've lost it. Right, so it's what we call NAND memory. It's what SSDs are made out of as well. Okay, but the big difference is it can retain its contents when power is removed. That's what you've got to say for that. There are other ones, speed and things like that you could maybe talk about, but what they're asking about, and you can see it leads on. They were asking about RAM and ROM. So it's leading on from that question. Okay, moving on. Right, this was universally awfully answered. Okay, from the number that I marked, I kept like crashing my head against my desk. Right, solid state device, an example. Right, some people threw it away because they put USB. You were lucky that the mark scheme was generous about USB stick. But please try not to say USB stick. Try and say USB memory stick. Don't say USB stick. That could be one of those things that lights up that you see on your desk. A USB stick. You could have a USB lightsaber, couldn't you? Which you could describe as a USB stick. Right, so they wanted solid state disk drive. Don't say hard disk. A lot of people kept putting hard disk for this. Hard disk is not a solid state, that's a magnetic device. Isn't it? Mechanical magnetic device. Which then went on to screw this next part of the question. Because they're related, aren't they? Primary or secondary storage. So, depending on what you said, if you said like solid state disk drive, or you said USB memory stick, you're going for secondary storage. What could you have said for primary? Yeah, ROM device. So that the BIOS might be stored on flash memory, mightn't it? Yeah. And that we would call primary because CPU can access that. Okay. But yeah, that was that was an interesting question because people just totally screwed this up. Totally. Don't get that. That's really weird. Right, this question. Right, I'm saying I'm not going to go through what the answer is, but these questions have like morphed into this format. They've told you what to talk about. So you must make sure that your discussion covers, and it is a discuss question because it says discuss, which means you need to contrast, don't you? If you're discussing. No one's saying what the answer is. They're not bothered about that as long as your conclusion leads off of your discussion. The mistake that a lot of people are making with this is they're going, the first sentence, they're going, I think you should use solid state. No, it's a discussion. Discuss it all first. Because if you start off with what you're choosing, it then skews your discussion completely. So if I was doing this, what I would do is I'd say, right, I'd talk about the portable qualities, and then we're asking us about optical storage, so like mini discs and CDs and all that sort of stuff. Okay? Which are quite portable, but they're a little bit bulky, aren't they? So we've got that contrast we can talk about. Robustness. CDs get scratched. You can't scratch an SSD unless you really try hard with like something like a grinder or something. Okay? So on robustness, you need to talk about that. What are the physical properties that make them robust? Capacity, you must always think in terms of the task. If we scroll back, this question was about, I think, something to do with about 5 gig of data or something. Yeah, 5 gig of data. You can get 5 gig of data on a DVD, roughly. If you've got a Blu-ray device, you can get 50 gig. So you can't say, oh, there isn't enough space on an optical drive. There is on certain times. So you're talking about capacity. It tends to be related to cost, doesn't it? And this is where our little friend, the SSD, gets walloped. Because per gigabyte, SSDs are a fortune. Optical storage is peanuts in comparison. You know, you can get DVDs that will load 5 gig and they don't cost much at all to buy a DVD. Not that anyone uses them anymore because of the other two issues. Okay? For transferring. But once you've chatted about those, you can then do your conclusion. So whenever you get a discuss, always make sure, if they've given you some pointers, talk about them. Maybe talk about them in that order. What you mustn't do is bullet point these. I know in some of the subjects you're allowed to do that, but you will throw all your marks away because on the mark scheme they're looking for written quality when you're doing these long form questions. Okay, so that wasn't a hard question to answer, but some people just like millied around a bit on that one. Yeah, waffle is what we've got to wean out of you.
I do.
And shall I tell you the other thing? Unusually for these questions, there was a hell of a lot of space. They gave you nearly 2 sides. So they're saying to you, just explore it a little bit. If you get given a load of space, they want you to put some stuff. Not keep endlessly repeating yourself, but make a point and make my good solid points. Talk about it properly. Right, the last one. Whenever you see something that says show your working, you've got to show working. If you don't, you're throwing the mark away. Yeah, the question's easy to get the answer, isn't it? It's not hard. But you must make sure you do some working out, whatever the hell that is for that question. Must show working. Right, this was universally awful, this next question, because people didn't read the question. File management. And it said, identify 3 ways that this person, and they're trying to be hit with the name Xander. Or maybe they're a Buffy, they're a Vampire Hunter fan or something, the example. Who knows? Whatever, they come up with this name anyway. Right, file management. That's all the stuff to do with organising your files. But we need to be specific. There was a lot of waffly answers on this. Okay, so file management is organising things into folders. Organising what into folders?
Documents.
What is he using it for? So it may be, yeah, his documents, his applications he might be putting in folders. Things to do with copying files around. But you need to, you can't just say copying, you've got to say copying his files from one folder to another. You use the file management stuff to sort your files. You know, sometimes when you're looking for files, you go, I can't find what I'm looking for, let's make them alphabetical. Or let's do, I know I did it recently, let's put them in date order. And all those things are file management facilities, but you've got to make sure you give a reason. It's asking how he can use it. So you can't just say sort, delete files. An easy way of deleting files, you can highlight them and delete them. But you need to say that. It's all about those things. Remember, this is all off the back of the operating systems. So you've got to remember those core facilities of an operating system. File management is one of those jobs. User accounts, security, application management, memory management, storage management. All those resources, that's what you're coming back to every time. Right, and then we had compression. And this guy's messing about with images. And it said, and the key word, explain, and then immediately following how. Alright, so they want to know how. So you have to talk about what methods you could use to compress. And a few people like sort of said the right things, but in order to explain how images work, you've got to talk about pixels, haven't you? You've got to explain that a picture is made up of pixels. And you've got to explain that each one of those pixels has got a colour. And each one of those colours is represented by some binary number, isn't it? And the number of bits and the colour depth. So one way that we can simplify an image to make it smaller would be to change the colour depth. So if we're using 8 bits for every pixel and we say, well, let's just use 4. That's going to have a consequence to the number of colours, but it will reduce the size of the image by half, just doing that. Some people said about averaging out some pixels, so like grouping together, so you drop the resolution effectively. But those are the things that you've got to say. It's super important, this and the audio are 2 really important things where you've got to be specific about the processes involved. Okay? You could have gone on to explain run length encoding as well, couldn't you? You know where you say, like, if we've got 15 black pixels following each other, we say, right, we've got a black pixel and there's 15 of them, rather than have 15 individual pixels stored. Okay? But it's really important that if you're talking about images, just like when you're talking about sound, you use the correct keywords. All about keywords. When you look at the mark scheme, you'll see, you'll go, oh, right, yeah. Keywords. Keywords keep coming up, and then explain the keyword effectively. Okay? Right, the last bit, generally quite good, but there's a few people don't know what a utility is. Okay? Remember, we've got 2 types of software. The applications that we want to run, and then all the other guff that we'd rather not get involved with, but we need to keep our computers going. All right, that's the utility software. Who wants to understand and know about virus scanners? I'd rather not have to have them, but we need them to keep our computers running. Malware pickers, we need them. Okay, defrag is not so much, but everyone puts defragmentation down. It seems to me that your default choices seem to be, when you answer these questions, is defragmentation, virus scanner. What do you think about utilities? But the stuff they've just been asking us about, there was a student that said compression software. We've just been asked about that, and it said other, to other. So really watch for that. Make sure you're not giving an answer that you've already been given. Okay? They tend to do that quite a bit. So they're going, oh, let's talk about some operating system stuff. Now let's talk about some utilities, and then just finish it off for us. Right, the problematic question. We know, because we're really clever, that neither of these are embedded systems. This is where we have to mitigate against mistakes in exam papers. They will always make sloppy questions or downright wrong questions. But you can tackle these questions still. So, looking at this, what I would tend to do, my eyes would be, I go, yeah, laptop's a general computer, isn't it? General computer. I can run anything on that. So it's definitely not that. There's only one other answer, smartwatch. They don't mean smartwatch. They should not have used that word. Smartwatches, these days, are full-blown computers. You can run general applications on them, as long as they've been designed to fit inside the shape of the watch. Okay? So they didn't mean smartwatch, they meant something like a fitness tracker. Some of this got like a focused purpose. No, I'm talking about smartwatches. Oh yeah, I'm going to walk around with a dishwasher on my arm. Yeah, I've got a smartwatch here by Hoover. He catches on fire. No, Adam. Right, so we need to think, right, if I was answering that, my immediate instinct would go, no, they're both wrong, but they obviously meant that one. Okay? And then it matters when you come down to this, that you give a solid definition of an embedded system. And please stop saying that an embedded system has one function. No, that's cobblers. It's got one purpose, to control the device it's in. That's what an embedded system is. But it might have multiple functions. Please stop saying it's got one function. It's got one purpose. So if this was a fitness tracker, like a Fitbit or something, you'd say, right, well, it's all to do with like health monitoring and recording stats and then showing you those stats back. And maybe part of its functionality is to connect to a computer to transfer the data, upload it to a website. But it's one purpose. The purpose is to work with the device it's embedded in. That is what an embedded system is. Not single function. And I know some of the resources say single function, and that's wrong. It's single purpose. They're getting the words mixed up. Single purpose. So yeah, it's definitely not a laptop, because it's a general purpose computer. But yeah, bad question. I know from talking to the students when they came out of the exam last year that they all was like, no, that question. But they all said they obviously meant the watch. Like if you think about an Apple Watch, it's basically just an iPhone with a cut down screen, isn't it? The only thing it hasn't got is it doesn't do the phone calls. It uses the phone to do that. It tethers to it, doesn't it? So it's all a bit crazy. Right, okay. Software. Our favourite thing, proprietary software and non-proprietary software. That's what this question was mainly about. But it starts off with a nice ethical question, environmental question. 2 marks is all it was. So describe the environmental impact. Most of you went down the right route. Packaging. Yeah, you've got to produce that packaging. But you must always make sure you're talking about resources being consumed. Because that's what we mean. So packaging, to create it, And then some people did put the other end of the game, which actually when you've finished with the packaging, what happens to it? Goes in landfill. Does it get recycled? That all to do with the packaging, but a few people did mention things like, if you've got a physical game, you've got to transport the thing, haven't you? So, yeah, you've got to get a truck. I'm still dying. You've got to get a truck, and that's petrol and cost, all those costs associated with pollution and things like that. Even producing the packaging, you've got to power a factory to make them, haven't you? So, it was a bit of a weird question where they wanted this and it was like, yes, I can write tons about this and on 2 marks. So do not go on and on and on when a question's only worth 2 marks. You're eating time. Remember, you've got just over about a minute mark. So the questions that are like throwaway, like that nice little ticky ram-rom one, you're banking time with those sort of questions, aren't you? Ready for these longer ones. Okay, last bit on this one. Proprietary and open source. Some people got these completely wrong way around. Remember, if you've got code that you want to protect, and a game in general is something you want to protect, then you don't want it open source. Because anyone can then take the source code and like change the copyright notice or something and say, hey, look at this game I've made. And then put it on iOS. Like people do. Okay? So if you make it open source, everyone can... It doesn't mean they're allowed to copy it, remember. Open source because you have a license. And you say, right, you can distribute this, but you're not to make changes and sell it as yours. It's mine. I'm the owner of the work. But when it's proprietary, no one can see the source code without a lot of work. Okay? So generally, if we want to distribute software and make money selling it, we will sell it in proprietary format. Just like when you buy games. You don't get the source code to, I don't know, Horizon Zero Dawn, do you? When you buy it for the PlayStation, you're downloading the binary, the executable form, which is what a proprietary setup will allow you to do. So you can give your program away. So I'll be writing a game in the next couple of weeks that I will give away. But I'm not going to give the source code away, I'm going to give the binary file away. So that's proprietary. Someone could reverse engineer it if they could be bothered. Okay, but I will retain the source. Because if I gave the source out, anyone could just like recompile it and do something with it. One of the problems of languages like Python, because you interpret it and you can see the source code. Okay? Always make sure you getting that. It's not about can you remember what proprietary and open source is, it's can you justify the choice. Nearly every single question on this part of the paper has been justify, hasn't it? Explain it away. So we've got to do this, gents. Okay, let's move on. So the algorithmic questions. Right, the first one screwed everyone up. Explain sampling. Remember what sampling is. It's capturing the sound level, the amplitude, the volume of your sound. That's what sampling is. So we take a reading and we store it. But we have to do several samples, don't we? We continue to sample. So we do it over a certain period of time and we do it at regular intervals. So we can go from a waveform to a snapshot at that point. Do a diagram. If you're struggling to explain it, do a diagram. So you can say like amplitude. You can state sample point. Okay? So we're taking a measure. That's what sampling does. Measures. It measures the amplitude of the waveform, the sound wave, at a particular point in time. Take enough of those samples and we can reasonably reproduce the original sound. But it's really, really dependent on how often we sample and what else. What's the other thing we have to be careful of when we're doing a sample? So we worry about how often we sample. What's the other thing we have to worry about? It's a bit like the colour depth for a pixel. the sample size or the sample depth. So how many bits do we use for each sample? If we use 1 bit, we could say there was a noise or no noise. That wouldn't be very accurate, would it? You'd end up with a big square block. The noise, no noise. So we have to decide how many bits. With CD quality sound, remember, we use 16 bits for every one of those samples we take. So if we take 1,000 samples in a second, we're going to have 2,000 bytes every second. Okay? But we have to remember these keywords. Right, so that's what they wanted you to talk about. I shouldn't have written on the board. But, if in doubt, draw a little diagram for the sound sampling, always. Because it allows you to then annotate to say, like, oh, this is how often we sample, that's that frequency thing. And that's what the next bit was about. Right, they're increasing the sampling frequency. Okay? So, and they said, just define sampling frequency. So, all sampling frequencies is how often we take a sample, isn't it? And we tend to refer to this as how many samples per second, which we use what units? Hertz. Okay? So, with CD quality sound, 44,100 samples per second, or 44.1 kilohertz. Okay? You can go, this wasn't a very deep question, it was only 1 mark. You can go into that the higher, and some people did, they said that the higher the sampling frequency, the more detail you can pick out in the sound. Because you're going to pick up higher frequency responses. Okay, but it was only a 1 mark question. Again, don't go on and on and on and on when a question is for 1 mark. If you've made your point, move on. Okay, and then next one, another one of these ticky ones. Tick 2 boxes in total. Okay, for this one. So, the effects of increasing. So, the more samples we take, the bigger things are going to be. We're going to have more data to store. Okay, so we had size of the recording will be smaller. No, it's going to get bigger. The size of the digital recording will be larger. Yes. The quality of the playback of the digital recording will be better. Yeah, if we sample at a higher frequency, we'll capture the detail in the high frequency sounds. Okay, so it should make the quality better, up to a point. Okay, the quality of the playback will be worse. So this is quite an interesting one because there were contradictory statements. So you could really sort of double check yourself when you were answering that one. Only 2 marks. Right. How do bitmaps get stored in binary? Actually, related to the other question. Now, remember, these were a pair of papers from last year. So, on the theory paper, they had a question about images, because they was talking about compression. Okay, so a bit cheeky. And then on this paper, they're asking about pictures again. So there was a little bit of crossover between the 2 papers there. Compression is a paper 1 topic, but images is a paper 2 topic, but obviously they can drag them over. So be aware of that. Don't think, oh, got asked that, they won't ask me that stuff again. So again, this is just talking about organising things into pixels. What does pixels stand for? What's it short for? Pixely. Pixely. No, it's picture elements. That's what it's short for, which hasn't even got an X in it. There you go. Go figure with the old computer scientists, eh? Yeah, so you're talking about the pixels, you're talking about palettes, you're talking about colour depth, and how we can represent larger palettes if we use more bits for each. So, standard computer formats, we use 24-bit colour. So we use 8 bits for each colour. So 8 bits of red, which gives us 256 levels of red. Same for green, same for blue. But we've moved on to UHD colour now, which is 10 bits. So you get 1,000 reds, 1,000 greens, 1,000 blues. It's not as straightforward as that because we don't need the same number of red, green and blue. So you can like prioritise. There's loads of different bitmap formats. If you ever get into graphics programming, you'll realise that there is loads of different ways of storing pixel data. But that's what they're asking about, pixels. Talk about pixels and an array of pixels. Talk about colour depth. Talk about palettes. Remember, we can switch palettes. But it only wanted 3 marks, so it's just those 3 things to talk about, really. Right, this one, universally, everyone makes a total hash of this question. Why do we use binary in computers? Because the computer is built out of switches, isn't it? We can represent on and off 2 states. So binary is a perfect fit. Because the computer can represent it easily with a switch. Transistor is our switch of choice. So you can always talk about transistors. That's what computers are made up of. All your logic gates are made up of transistors. Your NAND memory is made up of transistors. So binary is perfect. They just go together. That's what they're asking. That's why we store things in binary. Not because it's easy to convert, like some people keep saying. It's easy to do. It's easy, you've only got 2 things to worry about. Yeah, alright, whatever. It's not that. It's not about how easy it is, it's about how practical. Okay, right, next question. Lossy compression. Remember with lossy compression, we throw data away. If we throw data away, we cannot get it back. So, why do we throw data away? Because it allows us to get better compression. We can squeeze things down more. Okay? Why is that an advantage to a website? Right, if something's small, then the time for transmission is reduced. If you've got a 1 meg picture and you can squash it down to 100K, then it's going to take 10 times less time to download. We're talking, it's all about movement. How much memory it takes up and how much time it takes to transmit. Okay, we're talking about a website. So the size of all the stuff on the website makes a difference. We've come a long way from when we used to have dial-up connections at 1,000 bits per second. Okay, when we just didn't even bother doing images, we just sent text around. To the first websites that had pictures on, and then took forever to load, about 20 seconds, while you were watching the picture draw on the screen. You might as well have done it with your crayon. Okay, to going the other end and people expecting everyone to have fat broadband connections, so they've loaded them up with tons of graphic. Okay, so the smaller the better. Because it matters on a website, doesn't it? People do not hang around. If I'm on a website and you go, you go back. Pick another website. Unless you're forced to use it because you're using it as one of our websites and it's like, oh God, every time I go on it. Okay. But in general, the advantages of compressing something is so that the transmission time drops. The disadvantage with lossy compression, there is only one, and that's you can't get the original data back. So the quality is dropped. It's whether that quality is acceptable in the circumstances. Alright? But it is about the loss of data. Does it matter? Okay? In this circumstance. It might be that, I mean, we haven't got much detail here, but it might be a thumbnail. So we massively compress the thumbnail because that doesn't matter, and we can always click on it and get the full size image. Just like when you run galleries and things. They're all like that, aren't they? You know? So even if you're on your OneDrive and you're looking at your pictures, it doesn't give you full images. It gives you compressed versions, and then you click on it, and then you realise how slow the internet connection actually is. When it's like, drawing it on the screen. Okay? Super important. Compression always comes down to the same thing. Transmission time. Whether that's copying from a hard drive, or whether that is going across a network. Right. Question 2, I quite like question 2, and you all did pretty good on it, to be honest. We got a flowchart. Following an algorithm is the question, isn't it? So it is just about logic. It isn't really a computing question, I don't think. Because anyone can follow a flowchart because they're quite nice and simple and the logic is there. You don't have to interpret it, you're just reading it. Okay? So the question just said, okay, if these were the two inputs, what were the outputs? So it's just a matter of following it through. Most people got that bang on. There was a few people screwed up a few numbers, so I don't know what happened there. You need to look at that. Remember, you've got no calculator, so they tend to not give you nasty numbers for anything. Unless they do the binary conversion, they might give you some horrible ones. But yeah, that is just a matter of following it through. You can't really learn to do that. You've just got to be careful and double check. Right, writing it in pseudocode though. So we want to write the same algorithm in pseudocode. So we're converting a flowchart to pseudocode. The first thing, whenever we do input, we need to store input. Which means, when you're literally taking a flowchart, you can't just put input X. Some people did that. You've got to say like, well, I'm going to store something in X. That's going to be my input. Same for the Y. I must write like that. So I'm saying, get some input, store it in X, store it in Y. Okay? Whenever you're doing input, that is marks. Marks got thrown away by some people for that because they just put like input X. We don't write that in pseudocode. You can write it on a flowchart because you're saying where the input's going, but that's not how we write pseudocode. And then the rest of it is just following it through. Remember what these diamonds are, they're effectively ifs, aren't they? So I don't know what the answer to this is, but I'm just going to follow the logic through. So I'm going to do that if first, because that's the first thing that happens. So I'm going to say if X is greater than Y, and this is what you've got to be careful of. When we do an if, the thing after it is the true part, isn't it? If that is true. So if we look and follow the true part, it goes, oh, actually, we've got another decision to make. So if I saw a flowchart, what I would do to myself, I would write, so there's an if there, there's an if there. Okay, so I know. So I'm going, right, okay, I'll come back to this. I'm not going to worry about that yet. I'm doing the true bit, because that's the bit that comes next. And the very next thing I've got to do is an if. So I'm going to do another if. And I'm going to indent, so I'm making it easy. And I'm just going to say, what's the decision? Is X less than 12? If that's true, I output X. So I'm going to say, okay, when that's true, output X. If it wasn't true, that's what the false bit says, oh, output Y. So I'm going to put an else, aren't I? So I'm going to say else, output Y. So you can annotate all over this. So you could put on wherever you've got a false, you can say, oh, that's an else. That's an else. Okay, just so you've got it as a companion. So I'm going to come back. So I've done this part of the diagram. That was if that was true. Now I've got to do the else part. So I'm going to do an else there. And it said output Y times X. Yeah, well, I don't know what this is doing. It's not important. Output Y times X. And I'm just going to literally put the same thing down. And then it ends. From all those points to all that, so I'm just going to stop there. That was all the marks. Okay, so if you get a flowchart and you've got to convert it, annotate it a little bit so that you can see what elements you're going to build in pseudocode. But the input thing is key. You must show that you're storing it in a variable. And again, when you look at the mark scheme for this, you'll see that they didn't care if you changed all the names. Because it doesn't matter, as long as the logic is the same, they don't care. So that was quite a nice, solid question by most of you. Those people that didn't, that's really something you've got to work on, because that was easy marks. 10 marks for that question. Very nice. a good booster. And if you look at the grade boundaries, 10 marks is a boundary. Right. This was a funny question. In the fact that we haven't done this topic yet, okay, so it was interesting to see who revised. Well, you shouldn't have had to guess, Adam, you should have revised it. Right, translating high-level code into machine code. There are two ways. The compiler, which takes our source code and turns it into executable code, which is what we do when we're building games, generally. And the other method is the interpreter, which takes our program a line at a time, checks it and executes it, which is what Python is using. Okay? So with the interpreter, and we'll cover this again anyway, but with the interpreter you're executing and checking line at a time. So you're like, look at the code, oh it looks alright, execute it. Move on to the next line. It looks alright, execute it. Look at the next line. Oh, no, there's an error. Stop, tell the user. Which is why when you're running Python, your program can go so far and then crash. And it goes, error, because it's gone, oh no, I can't execute that, it's rushed, you've done something wrong. With a compiler, if you've got one mistake, nothing runs, and it'll just stop and say, there's a mistake, mate. Okay? But in general, Python runs in an interpreter. So it does the line-by-line access. When we're doing other languages like C#, C++, and Java, they're compiled languages, so they do a full check of the whole code. So any errors that you've got are going to get caught. An interpreter, you can do a lot of hacking. You know from doing your projects, you can hack away and get it to run up to the point where it falls over. All right, but that's interpreting and compiling. We'll come back to all that. Right, conversions, generally fine. You just got to check. There was some nonsense to some of these. The hexadecimal's really getting on my nerves. Right, I've got A3. I want to write in denary. You've got two ways of doing it. You've got the way that if you had your calculator would be easy. A times 16 plus 3. But we ain't got calculators. Although you could have done that one, because what is A? 10. So you could have done it that way. Okay? But the other way is to say, right, well, I've got my binary. That makes it easy. So I'm going to write down A. Remember, each hex digit is 4 bits. And I'm going to write down 3. And then I'm just going to put my column headings down for the ones where I've got, oops, not a 3, Eric. And then I'm going to add them up, and I'll get 163. Okay? So, hex and binary, remember, they work really well together. Hex is a really compact way of writing binary. That's why we use it. Not because we want to be bods, and we want to go, hey, I know hexadecimal, and I'm going to call it hex, so you don't even know what that is. You know, that's not what we're doing. We're doing it because it's nice and compact, and if you do it a lot, you can see the binary patterns. So if you're doing any assembly language programming, or you're doing any colour stuff in HTML, that's why we use hex for that as well, because it makes it easy to see. The last question, oh, notice this show you're working on these two. So again, we wanted to see some working out, not just, oh, I'm really clever, I can do it inside my head. Yeah, brilliant, you've lost a mark. You're so clever, you've thrown 2 marks away. Okay, so, always think about it. Right, the last bit. The symbol is exponential. Now they gave something, and you guessed correct, Adam, it was the power, raising to a power. You knew it. Yeah, well, you should know it from maths, shouldn't you? Yeah, you should know it from maths. Right, so it's just a to the power of b. And they say, what is the answer? Well, this was an easy question, wasn't it? It's not even a computer science question. Okay, so hopefully, some of you did screw that up completely. And you just think, right, well, you need, just remember this is, computer science is cross-discipline. Right, and then the final question. Right, if you're adding up, you've got to show carries. you've got to show the carries. Okay? We want the answer, but we want to see the carries. Don't we? Wherever you put them, whether you put them underneath or you put them next to it like I do, I don't care as long as it's clear. What other thing have you got to worry about when you're doing arithmetic? Yes, Louis? Right, overflow. We need, if in this case we had two binary numbers that had different lengths, didn't we? So these were like implied zeros. If when we add up some numbers, let's say we had this number, right, 7 and 9, okay, and we added those together, so we went 1 and 1 is 0 carry 1, 0 carry 1, 0 carry 1, hang on, I'm going to get my notes and my ones all around my ear holes, 0 carry 1, 0 carry 1. It's important when we've got fixed numbers of bits that we say the answer is this part.
So what if you turn the binary numbers into binary numbers?
No, because we're not interested in can you convert. That's what the previous question was about. Right. That doesn't help you, Adam, because you don't get your working out marks. And if you screw the conversions up, you're going to totally screw it. Right. If we get this situation, that is our carry. It's not part of the actual number. Carpy, sounds like some sort of fish thing. Right, show it like this. And I would always ask you, for the examiner, I would put answer and I would repeat the answer. Okay, so I'm making it clear to that examiner that the answer is here. It's here. It's not randomly these bits that I've drawn on the corner of the paper, which is what I sometimes find when I'm marking some of your work. Make it clear. In maths, it wouldn't be acceptable to have random numbers on the page as the answer, would it? Do you have to like double underline and all that sort of guff? We used to have a maths teacher who used to be brutal, and if we didn't double underline the final answer, we got nothing.
What?
Well, but it's discipline. You're not marking it for you're not writing your answers for your teacher, who knows that you're a total lazy donut. You're answering for an examiner who don't know you, hasn't got much time on their hands to get all these marking done, so they're just going for it. You're making it as clear as possible. They won't spend ages hunting for the ruddy answer. Okay? And like just get, oh, that looks like the right number. Maybe it's that is the answer. You can have as much working out as you want, but make it clear. Right, the last one, you obviously need to know that it was an OR game. Okay? So they ask you just to fill the truth table in. Just got to learn these, gents. So we have got so far 0 and 0 is 0. Yeah, that's good. 0 and 1 is 1. 1 and 0 is 1. 1 and 1 is 1. Easiest 4 marks on the whole paper. That did not take 4 minutes to do either. Okay? But there are some things where you've factually got to know stuff before you can even attempt the question. But most of these questions were explain, describe. Okay? That's what we've got to nail down. We have got 6 months to nail this. And we can nail it. Most of you, when you look back through that paper, you'll go, I was so close to actually getting the right answers here. And it's just little things. And it's like, you're doing it on quite a lot of questions though, so it all adds up. Or subtracts from what your total could have been. But you can all make massive improvements, definitely. I think. I think the potential's there. We've got to release that potential. Right, I'll stop that recording.